Okay, so today I'm going to be talking about a problem that we've been working with recently at the company I worked for, which is Planet Labs. Now we're just Planet, so we're branding ourselves. But it's one of these kind of interesting little problems that pops up, and it's the sort of thing that sometimes falls by the wayside, but I thought it would make a really interesting presentation. And it's actually something that I was hoping to have an open source library available when I gave this talk. I was going to give a lot of examples, but that's still waiting on approval. But hopefully very, very soon there'll be a library out there to implement this as well. So let me just say quickly a little bit about kind of the overall field I'm working in here and what this is. So Planet, as a company, we make small satellites. They're about 10 centimeters by 10 centimeters by 30 centimeters, and we have a lot of them in orbit, over 120 right now, with 44 more launching tomorrow, no, day after tomorrow. So really quite a few. What I do in general, I'm on the mosaics team. So we try to take all that satellite imagery. They're taking essentially pictures. They're basically just visual and near-infrared satellites, so it's more or less a fancy camera, and make one nice, seamless, pretty picture of the entire planet out of tens of millions of little individual pictures, and do it at a very high cadence and at scale, so fully automated. So my coworker Amit just gave a talk on the mosaicing process in general earlier today, so if you saw that, it's a bit more context. I'm not going to say a whole lot about it. So one other little quick comment. I'm actually a geologist. This is not normally what I do. So a lot of this stuff has been kind of new to me, and this is one of the interesting little problems that pops up. So what I'm going to talk about today is color correction. So we're taking these images, and we need to do a lot of different corrections to try to normalize them. It turns out that since we're worried about having a nice visual seamless image, a lot of this is not the sort of normalization and more rigorous scientific correction that I'm more accustomed to. It's much more ad hoc kind of empirical methods because we want to make things look pretty. And so it turns out to be a lot of really interesting problems. So here's the fundamental problem. Remote sensing data is really inconsistent. It's not this nice uniform stuff that you can just start immediately, comparing images from all sort of different things. You can to some degree, but you have to worry about a lot of what's going on. And a lot of that stuff is not easy to immediately detect in the sensor. So one of the big things is atmospheric variability, where we have a satellite in space. The Earth's atmosphere is in between that and the ground. The atmosphere varies a lot. Now, if we have a nice, very rich instrument, something like MODIS or VIIRS, you have a lot of different sensors, you can very rigorously correct for what happens to the signal as it propagates through the atmosphere. If you just have visual data, you can't really distinguish what part of the image is from the atmosphere scattering light back and what part is the real ground. Another thing is that you just have real changes. If we're making a mosaic, we may be using a month or 2 months or 3 months or a week. It can be a lot of different time spans of data, and things change in that time. Trees get greener, grass changes color, fields get brown. So there's this real change on the ground. We need to make it look like it didn't happen in a lot of ways. And then we also have sensor variability. The satellites are all a little different. We can correct for some of that. Other parts we can't fully correct for anyway. And then we have minor little things like lighting conditions. The list just goes on and on and on. There's a lot of this that leads to variability. But here's the problem in a picture. So hopefully you can see that okay. I can't really see it from here, but what you're seeing is data that's been run through kind of all the normal corrections. We just have left the atmospheric component in because we don't have a good way to rigorously correct for that. And you see all these, it's multiple different scenes, multiple images, and you see how variable they are. They're kind of all over the place. You can see all these obvious jumps where the different scenes come in. It's a region in China. There's a lot of haze there. There's a lot of atmospheric variability. But we need to do something to correct for that, make it look seamless, make it look uniform. And that's really what the problem is that I'm trying to solve here. So the solution is color balancing. This is really just purely an empirical method. We have a reference image that's from some other satellite, something that can image a very large area at once, and we can really rigorously correct for. So things like MODIS, Landsat in a lot of cases. And we just want to make it look similar to that. That's our ground truth. Try to match it to that. If we match it all to the same image, then the images look pretty similar. And when you do that, it works really well. So on the left, we have that original image with lots of inconsistencies. On the right, we have actually the image corrected with, it's multiple images, but corrected with the method we're talking about today, and then some very nice seam line removal that Amit briefly mentioned this morning. But basically, we normalize the appearance of these images through kind of this empirical process. And so Normally, the way this would be done, it's not a new idea, it's been around for ages. And the way it's been done for a very long time is with histogram matching. And that may seem a little outdated if you're kind of in the computer vision field and a few other things, but in for geospatial data and remote sensing data, that still is the most part of the state of the art. It's what people use the most. The basic idea is you take a histogram of the reference image for the area that you're working with, and the histogram of your input image, and you force them to have the same shape for each band. That's it in a nutshell. It's actually pretty simple to implement. I'm going to steal from someone's Stack Overflow answer here. I was going to write up a short example and realized they'd already written one, and I figured I was lazy and why not just borrow theirs. So the basic idea here, we're using a Lena image as the input, but we take an image, we have some template we want to match it to. It doesn't have to be the same thing. It just needs to have similar content. And then we get the histogram of each. We make a cumulative histogram. So notice it always increases. And then we force, let me see if I can get my mouse cursor. Here we go. So this is our original scenes image, the red there on the bottom. This is the target image. And then we just basically come up with a transfer function by really just interpolating the target image, interpolating the histogram of the target image that forces this histogram to look like that histogram. And we do it for every band. The code to do that is actually really simple. Part of why I wanted to show this was just to show you can do this in a few lines of code. All you really do, you take the cumulative histogram and you interpolate it at each point. That gives you the transfer function that makes them look identical. It's piecewise linear interpolation. The point here is not to focus too much on the code, just to focus on the fact that you can do this with just a few lines of Python. And it's actually quite effective. I mean, this works extremely well when it works. And so some of the advantages, as we just showed, it's very easy to implement. It's quite fast. It takes a while to compute histograms, but other than that, the rest of it's very fast. There's no parameters. This is take an image, another image, bam, you're done. There's nothing here to tune. We don't need any location information. So we could normalize an image of the Amazon rainforest to an image of an African rainforest. It doesn't care where they are. And that's both a good thing and a bad thing. And it works really well so long as we have similar input. So what I mean by that is if I have a picture of this room with a bunch of white tables and yellow chairs, and I normalize it to a picture of a different room that had, say, a bunch of black seats and orange ceiling, I'm going to get really wonky colors in the result. Now, that may seem kind of obvious. The problem is, well, all right, first off, let me show you how it works when it does work. This is actually no color balancing on the top, and on the bottom, color balancing with histogram matching. It works great. So the problem is when we don't have the same content. Now, it would seem like with remote sensing data, we should always have the same content, right? We're looking down, we're taking a picture of the same place. So what changes if we're looking from outer space? There's all these, minor little things that hardly ever happen, like clouds and snow and seasonal changes. So, these are things that, needless to say, happen all the time. And so if we take and normalize an image with lots of clouds or snow to an image that doesn't have clouds or snow, we get all kinds of crazy artifacts. So just as an example of some of these, so at the very top we have the reference image. This is our color target. In this case, it's some Landsat data. It's basically an average of a lot of different Landsat scenes. The middle, we have the input image that we're trying to normalize, and then on the bottom, we have the result when we apply histogram matching. So the left-hand column, what you can see is we've got some snow in the reference image, no snow in the input scene, and we get this false snowy fields in the output. We can also turn clouds nice and murky brown. So we have no clouds in the reference, clouds in the input, and we get murky, soupy brown clouds. And then the really fun ones are when we have a lot of snow in one and no snow in the other, we can turn things really bizarre colors. We're basically taking the maximum value in each band, regardless whether or not that color occurs in the target, and then matching that back to the white that's in the input scene. And so you get crazy greens and pinks and all kinds of bizarre colors. So one thing I want to mention here, one thing it's done to mitigate that is that you do the histogram matching in a different color space. So if we did this in lab space or HSV space, it helps, but really what it does is it changes the color of the artifacts. It doesn't solve the actual problem. So you'll see a lot of people saying, well, you just need to do this in lab space, the whole problem goes away, or well, more likely in HSV space for this particular problem, but it doesn't actually help that much. You won't get neon green, you'll get purple. You still have this fundamental problem of different content. So here's another more severe case. This is actually from one of our December 2016 mosaics. This is published, still out there. We've never bothered to recompute it, but you can see these really severe artifacts. What's interesting, you also have these huge regions that were turned brown and green. Every single input seen in that region was snowy. If you were to look at that with no color balancing with a different algorithm, it would be almost pure white. So we're taking this area of Iowa and Minnesota in December, and surprise, surprise, there's a lot of snow. The color target doesn't have snow, you get weird things happening. All right, so I've said a lot about that. Clearly, we need a better method. That's why I'm here talking. That's the problem that I'm trying to solve. So some constraints on that method. We need to be able to handle snow and clouds. That's kind of one of the big things. Another thing is that we need to preserve the white balance. What I mean by that is if something's white in the input scene, it needs to remain white in the output. If something's black, it needs to stay pretty close to black in the output. And more importantly, but a bit more subtle, if we have these neutral shades of gray, we don't need to shift them very much. A light gray should not become light pink. And it's okay to become lighter gray or darker gray, or maybe, a little subtly visually different brownish gray, but we don't want it becoming something that's visually different from what it came in as. Another thing is that we actually have to stick with this empirical approach. Our satellites are, again, visual near infrared. To do really proper atmospheric correction, you need other instruments that we just don't have on the satellite. And so we need something that we can do with not a whole lot of other ancillary information. One other thing that I think people tend to overlook with this, it's very, very important that this is an efficient method. We have to scale this up to running globally in a few days for the entire Earth. So you take 10 million images, and we're going to run it on a lot of machines, but still, you need to be able to do it and with everything else that goes along in just a couple days. So that means that you're down to a second or so of processing time for the color correction. It's really not a lot. And not only that, you can't train something and then apply it because this is train once, use once. So it's not one of these cases where we can spend a lot of time up front training a model and then apply it really quickly. We've got to train it for every single image we put in because every single data set it's matching to is different. And that kind of limits our options. So let's go back in for inspiration. Let's think about how this is done manually. So normally, like I said, I make mosaics. That means I stitch images together and make one nice seamless image out of them. Normally for geospatial data, that's done more or less entirely manually. And the way that it's done manually is, if anyone's used like the curves tool in Photoshop or GIMP or any other image editing software, that's essentially what you do. You do the color correction there. So what you do is you're hand drawing transfer functions. By that I mean we're going to map a value in the input to a value in the output through some relatively smooth curve. And we're going to do that interactively and kind of see the result. It's also one other thing I want to mention here, because this will come up quite a bit. If you have raw data from a sensor, so it's like a camera's raw file, the sensor perceives intensity of light very linearly. So our eyes, on the other hand, perceive light very non-linearly. So something that's very bright versus something that's kind of, bright but not super bright, our eyes perceive them pretty close, but a sensor is going to perceive the real linear density and intensity, or difference in intensity between the two. So when we take something that we want to represent visually from the raw sensor data, we also need to apply this kind of broad correction for just how our eyes perceive light. So usually when you're doing this manually, you'll incorporate that. You could also work directly with visual data that's already been visually corrected, but for the most part, we're starting from the raw data here. So let's kind of mention that while we're on it. The reason I was mentioning that is this particular curve is an example of one of those hand-drawn curves. And you'll notice the very strong nonlinear component. Actually, a lot of it, this is a mathematical version of one of those hand-drawn curves. So what we essentially have, though, is 4 transfer functions. We have one for each band. And then we have a master curve that's applied to each band after that band's transfer function has been applied. All right, let me kind of restate that a little bit. What we basically do, in that case it was linear, so you notice the band curves were aligned, so we take some linear transformation and then we apply it. In other words, we're composing functions. So you think about it just in terms of simple functions here. The final transfer function is the master curve of the band curve of the input data. We actually do this through a lookup table typically when we apply it, but that's a bit beside the point. So what I want to focus on here is that we're taking this 4-curve function and we're actually making 3 transfer functions from it. These are exactly the same, just different representation. So this is the original, and we're just applying that gray curve to each of those linear curves to get this. That's really what we're working with. So That's what we want to try to model. We want to mimic this sort of manual process. We want to define a transfer function from 4 curves, a master and 3 band curves. And they need to be very smooth. That's one of the big problems with histogram matching. That's why it tends to do strange stuff, is that we don't have a very smooth mapping from input to output. So the other thing is that when we do this, we want to do it such that we minimize the difference between the reference image and the input image. That seems kind of obvious. We want to make them look the same. But how we do that turns out to be quite important. All right, so we need some way to mathematically represent these. When we draw them by hand, it's usually some sort of spline curve mapping. So with a spline, you're defining points, and each one has multiple parameters and can have multiple parameters. Either way, you have a lot of different points. Even if it's only 1 or 2, it turns out to be quite a few parameters. If you use splines to represent these, you have a lot of flexibility, but then you wind up with very high-dimensional solution space to work in. Using splines for this turns out to be a real pain if you're trying to treat it mathematically. You want to reduce the dimensionality, just have a few parameters. So ideally, we don't want to use splines like GIMP or Photoshop is using. We want to come up with a simpler mathematical function that still has the shape we want and some flexibility in that shape. One of the ways we can do that, though, is the corrections we're interested in, these smooth corrections, the sort of things that you'd want to do to match an image, correct for atmosphere, and maybe change some of the seasonality effects a little bit. You're not dealing with the full possible range that you might with, say, color curves in Photoshop. You don't want to tweak the highlights here and the midtones there. We want something fairly simple, so we don't have a lot of variability. So all we need to do is find a function with the right shape and give us some way to tune that a bit. All right, so we can make some assumptions. The band curves will always leave us linear. That's a good assumption for this particular problem. They may not have the same slope. They can be different. The reason is that what appears white in the input image is something that needs to be kind of tuned a bit. So this is something where someone's taken and manually gone, okay, for this satellite, the red sensor is a little brighter than the blue sensor, and we need to kind of correct for that. Part of that's done automatically. Part of it is just purely a visual thing. So we'll keep those linear. We have to have a positive slope, and there are some constraints on what that should look like. What I'm really saying is that if I put in pure black as the input, I don't want to get out white as the output. That's really what these constraints come from. So let me actually show you what I mean visually by these. So here we have 4 examples. Only one of them is valid. All of them have positive slopes. So just saying, okay, we need a positive slope isn't that good of a constraint. We actually need to say a bit more. The far left one over here, it's invalid because black would be mapped to some middle gray color, and then some middle gray color would become completely white. This one over here would map pure white as black. Well, not quite black, but almost black. And then this one would threshold the image. We don't want these really steep slopes that are basically going to give you 0, 0, 0 white. You want to have some constraints on this. So what comes out of that is that a slope and an intercept is a terrible way to parameterize a line if you want to control those sort of things. There's interesting little mathematical tricks like this that come out of it. So it's much easier if we think about the line in terms of 2 points. All right, we can find a line from 2 points, no problem. We'll fix the y parameters of those points. So they're basically where y equals 0 and y equals 1. So then we only have 2 numbers to worry about for the line. So we can parameterize that same line in terms of a black point and a white point, basically our x0, x1, where it would map some value to completely black and where it map any value to completely white. Okay, a little bit of algebra here. We basically just take and solve for where y equals 0 and y equals 1 and get a slope and intercept. And then we're going to clip it. We don't want to be able to produce negative values from these. But it's pretty straightforward. The master curve is a little bit more complicated. So we need something smooth and monotonic. It can't suddenly, if we have our input image, if we go up in brightness in that, we don't want to have the output image decrease in brightness. That's what I mean by monotonic here. For raw data, we need to be able to limit it to a convex shape. For data that's already visually scaled, though, we want to be able to go back down to just a straight line, which would be the no change. And it needs to handle a lot of variability within that. So one thing that happens to have the sort of shape we want, for the most part, is the error function. And if you may recall, the error function asymptotically approaches 1 and -1 as we go to infinity and negative infinity. And so we can use just a portion of this function. So we'll take just a part of it. We'll say, okay, we'll use from 0 to like 1.5, and then we'll just scale it such that that value at 1.5 is 1. and we can go out to say 10, and we get a different shape. Just we use different portions of it. It shifts that bend in the curve as we go to higher and higher numbers. This is an alpha parameter I'll talk about in a second. It shifts that bend over to the left. We also may want to tweak kind of the way it bends, and so we'll apply a simple exponent to it. Give you some idea of what this looks like. In most of its comments there, I just want to point out basically we have an error function times some of our input values times some parameter, and that's taken to 1 over some power. Pretty simple function. And that gives us quite a few different shapes that follow the sort of trends we want. This is one of the tricks here. We find a mathematical function that can only give us shapes that we like. And the nice thing about this is it's very easy to limit to the sort of shapes that we might want in just our case with raw data to visual data. And that's the ones that are shown in darker blue there. We can just put some simple bounds and we get stuff that looks like the sort of curves we want it to be. So it's a lot of the tricks in this are just finding the right mathematical functions. All right, so we have a model. We have 8 parameters here, 2 for the master curve, 2 for each of the band curves. What are we going to fit it to? So keep in mind, this is geospatial data. We can take a point in the input and get the exact same point in the output. So the basic idea is that we're going to take and co-sample the reference image and the input, and then just kind of get a scatter plot. That's more or less what we're fitting to, but there's some wrinkles in this. So I've got a scatter plot of the input and the output. They're normalized to 0 to 1, and red, green, blue indicates each band. So we're more or less fitting the mathematical function to that. There's some caveats, though. We need to find some way to measure how well the function's doing. You know, we need a measure of misfit. And RGB distance is a terrible way to measure visual misfit. Just because things are far apart or close together in RGB space has very little to do with how they look visually in differences. So instead, we'll go over to LAB space and use delta E values. These are just basically the difference over the absolute value, and then a lot of fancy normalizations thrown in to make it visually representative. Fortunately, scikit-image does all the hard work for us. So we can get these nice visual misfits with really just a couple lines of code. Scikit-image does all of the hard stuff. So all we're doing is essentially saying, here's the sum of the, or well, mean in this case, of the misfit. All right, here's the other thing. We want to preserve the white balance. So there are a couple ways we can do it. All of them have to leverage a priori information we know about the image. So we have to know what the white balance is. For raw data, that's kind of tough. For data that's already visually scaled, you can assume that, you know, if we put in 255, 255, 255, we'll get white. For raw data, you can't assume that. So fortunately for our satellites, we have that information. So for each satellite, we can use that. And what we'll do is there's 2 tricks that we'll use to preserve the white balance. The first one is that we'll fix that x1 parameter. That was the top of the line. We're parameterizing the line. That's that top of it. We'll just fix that. That's the value that basically gives us white. We know that. Don't let it change. The next problem, or the next trick, is to take all the neutral colors, get all those grays, or everything that would produce a gray from our starting guess, and make sure we don't deviate too far. We don't want that gray to turn pink. So we'll just add those in, really, as extra points. So we have our original sampled bands, and then we have these new gray points, and those bigger dots. So these essentially fill in the rest of that shape. So we have constraints on where we have our data, and then we have constraints on where we don't have our data and where we know it should go. All right. So now we can define a function we want to minimize. We basically just want to minimize the misfit, but again, in CIE lab space between both the actual points and the white balance points. And then we can use some different techniques to optimize it. So in this case, it's a smooth mathematical function. It needs to operate quickly. Really, the best fit for this sort of problem is plain old gradient descent. It's nonlinear optimization. I know it's not fancy, but it actually works really well. So that's the basic idea here. We're going to use SciPy.optimize. We use a bounded solver, so it can't do anything too crazy, but nothing all that fancy. It's just we define a nice objective function. We have the functions. We minimize it. All right. I've talked a whole lot about all this. Let me show some examples. So these are exactly the same data as for a large portion of Europe here. I'm not sure how things are showing on projectors, but can you see the green patches on the right? Everything's brown as well. So we have a lot of snow. Histogram matching turns a lot of it brown, some of it green. It doesn't show it as snowy. This method preserves the snow colors, which is a big advantage here. Another thing, just on a global scale, exactly the same data in both of these global mosaics, something like 10 million images, actually a bit fewer for this one, more like 3 or 4 million, but several million images, identical between the two, just a different color balancing method. Notice how the robust balancing shows a ton more snow. It's there in both. The histogram matching is just hiding it. I don't know if you can see it from the room, but there's also a lot more clouds obvious in the tropics with the robust balancing. It's because the clouds are being turned green and brown in the histogram matching. So again, it actually works quite well. One other quick example, maybe a little hard to see this. So histogram matching tends to kind of blur things a bit, so we lose contrast in cities where we might have a lot of bright rooftops and the like. And so the new method makes sure that we preserve that full range of contrast, particularly in areas where it might otherwise go away. So the advantages, we handle clouds better, we preserve contrast. It's generally works pretty well, but there are also some disadvantages. It's optimized for this raw to visual transformation. It doesn't handle stuff that's already visually scaled as well. That's just a choice of the mathematical functions I made. It's actually less consistent than histogram matching. It will show more of real change. That makes it less consistent, but also it can just fail to come up with a good solution. If we have something that's really different, it can get stuck with its initial guess, and that causes inconsistency. So if one just sticks with the initial guess and one actually solves to a solution, they're side by side, it looks inconsistent. So there's a lot more that could be done. And that's what I think I want to emphasize here. Histogram matching has been seen as, I think, the be-all and end-all for geospatial data color balancing. And I think we can do a lot better. And there's still a lot more that can be done here. So if anyone has any ideas, I'm all ears. This is a problem that's surprisingly interesting. All right, one other quick note. Hopefully this will be out as a reference implementation and a library for it very soon. And be happy to take any questions if there's time anyway.
Thank you. Questions from the room? I think there was someone else with a mic somewhere. If you could help out. Sure.
It seems like what you choose for comparing your, like your test image, or I forget what you called it, but the image versus the image images you're trying to fix. Seems like that's a really important choice. How do you choose that?
Yeah, it's a great question. It's very, very important. It's a lot of what defines the actual color. So for these, most of what I showed was Landsat data. We basically take a bunch of data where we know a lot about the sensor and can do it well and make something that's corrected for atmospheric effects, and we try to get an average that reflects the current season. But we have to use a pretty broad range of months, so some seasonality. So ideally, we'd like to use other data. So we're starting to use more MODIS data, which has daily imaging at very coarse resolution. And so we can get a lot more imagery to stack up. We can get something that's more reflective of, say, like the month as opposed to the entire spring. And that's one of the big drawbacks to this. We need that reference image to be relatively accurate, and it's not always easy to get something that's relatively accurate. Sometimes it is, sometimes it isn't. But yeah, it's a really good point and a great question.
Any other questions? One in the back. There's a mic running to you.
Hey, sorry for being so far back. I guess like one of the major issues which you've been tackling is like applying the concept of histogram matching to like data which is in color space. Do you see any application of the like tricks you've found out to, for instance, data which is still grayscale but has different contrasts in like the template as the data you're trying to match? To give you a sense of the specific issue I'm thinking about, I'm doing brain imaging, and sometimes you want to like match different images of brains onto each other, and very often you end up having different contrasts between the brains you're trying to match. Do you think there's any application of this in that direction?
That's a really good question, something I haven't thought about much. I think the one caveat with that particular application is that you would need some image that's relatively correct and complete all the way through. I actually used to do 3D seismic imaging, which is not too different from that, and use not too dissimilar ideas for a lot of the matching you do in seismic, which is essentially grayscale. But you have to have large overlapping regions, and that this method does as well. So I'm not sure if your particular application would have the overlap requirements, but if it did, it might be interesting to try. This is really optimized for visual comparisons, and that's essentially, in a lot of cases with medical imaging, that's what you're wanting to preserve is the visual contrast. So yeah, it's a good question and something I haven't thought much about.
Okay, thanks.